Welcome back, students. So far, we have finished 10 lessons. And today, we will be taking up the 11th lesson. The lesson is titled, The Dual Nature of Radiation and Matter. And it is organized in a certain way in the textbook. But we are not going to follow that organization. We are not going to follow the steps given in the textbook. We are going to follow a different organization when we deal with this lesson. The reason is this. This lesson is like a detective story, like a murder mystery. And if I were to discuss this lesson with you from step 1 to step 2 to step 3 to step n, then you may not understand all the steps as they are laid out to you. But usually what happens in a murder mystery or a detective story is this. Once you know the climax, then it is easier for you to follow the details of each and every event that leads to the climax. So that is exactly what we are going to do now. We will focus first on the climax. And once we know the climax of the story, then you can come back to the individual events, individual steps that led to this climax. This is how we are going to organize it. So let me give you the climax first. The climax is this. It is Einstein's equation. Einstein's photoelectric equation, to be precise. But before we talk about Einstein's photoelectric equation, let me give you the backdrop of the whole thing. Let me give you the setup of the story. Then I'll give you the climax. Light was a mystery from the very beginning of human existence. And when scientists started to look at light in a rational manner, they first thought that light was a particle. It had particle nature. Particularly, scientists like Newton were great proponents of the theory. It's called as a corpuscular theory of light. Corpuscle means particle. So light travels like a particle. And that is the premise of the corpuscular theory of light. As I said, Newton was a great proponent of this theory. And many scientists believed that light traveled as particles. But then there were some phenomena which did not obey this particle nature of light, or the proposed particle nature of light. Those phenomena you have already come across, like the interference of light, the interference patterns that you saw in Young's double slit experiment, and then diffraction of light, and then polarization of light. These things could not be explained with the corpuscular theory of light that Newton and others proposed. Christian Huygens, as we saw in the previous lesson, was a proponent of the wave theory of light, But when he proposed at first, nobody took him seriously. But then, that theory was used well to explain the phenomena that we just talked about: interference, diffraction, and polarization. So these things could be explained with the help of the wave theory of light. So it came to be established that light was a wave, and particularly the Maxwell's equation. When you manipulated those equations given by Maxwell, it gave us the wave equation, which suggested that light was a wave. So all these things together established light as a wave, and scientists thought that the matter was settled, that light was a wave. So all was well for some time. And there were other experiments, other phenomena that people came across, which could not be explained with the wave theory of light. There are a couple of phenomena which are very famous, and they are the photoelectric effect and the Compton effect. And these two things could not be explained with the help of the wave theory of light. You are not studying about the Compton effect, but you are studying about the photoelectric effect. Okay, what is photoelectric effect? Well, you have a conductor, you have a metal, let's say. Then there are electrons inside the metal. They are moving around in all different directions because of thermal agitation. We know that there are free electrons in a metal, and those would be moving around because of the thermal agitation. But none of the electrons come out of the metal. Now why? Inside they can move around. But then when an electron tries to come out of the metal, then what happens is that the metal no longer remains neutral. Then a part of the metal, or the metal actually becomes positively charged, and then the electron is negatively charged, and the metal immediately will pull it back into itself. So it is usually difficult to get an electron out of a metal as is without applying an electric field or something. In an ordinary metal, even though the electrons are moving in all different directions, none of them come out of the metal because of this nature. Because when they try to come out, the metal becomes positively charged and attract the electron back into the metal. But if you give an electron sufficient energy, then the electron should come out of the metal. That's understandable. I may keep throwing stones upwards, then all the stones may be coming back to the earth. But then if I throw a stone with a certain velocity, with a certain kinetic energy, then the stone will go out of the gravitational field. We have studied about this. So likewise, inside a metal too, an electron, if it gets enough energy, can break away from the metal and then come out of the metal. So what is a good way of doing this? Well, if I shine a light on the metal, then the electrons will get excited by this light energy, and if they gain enough energy, then they can come out of the metal. So shining light on a metal is a good way of getting the metal out. But another way of doing it is heating the metal. there also you're giving energy. I mean, that is also light in a way. You see, it's infrared, right? Okay, so infrared light, which is heat, can get electrons out of certain metals. So basically this is the idea. So you give energy to the electrons, and if they gain energy, then they can come out of the influence of the metal. So that's the basic idea. Now, light is a wave, and in a wave, the energy depends on the amplitude of the wave. Actually, the square of the amplitude of the wave. We have come across this before. Energy, power, intensity, they are all directly proportional to the amplitude square. Frequency plays no role in that at all. But amplitude is what will decide the energy of the wave. So, if I shine light with enough intensity, then I must be able to get some electrons out of the metal. That is what I would expect, irrespective of the light. I can shine red light or a green light or blue light or yellow light, doesn't matter. As long as I give enough energy to the electrons, then they should be coming out of the metal. But when I try that is not what is happening. So what happens is that for a particular frequency, for a particular light, color of light, let's say, electrons come out. And for frequencies above this frequency, electrons come out. But electrons do not come out for light with a frequency which is lower than this threshold frequency. So let me put it this way. Suppose there is a metal. And let us suppose also that for the green light, it starts emitting electrons. And when this happens, if I shine blue light, the electrons come out, because blue has a frequency greater than the frequency of green. But if I shine a red light with whatever intensity, the electrons do not come out of the metal. This is baffling. Why should this happen? All it requires is energy. All the electron requires to come out is energy. And I'm trying to give it with red light, but it doesn't come out. If it starts coming out from green, then for any color which has a frequency greater than that of green, electrons come out. But for all other colors which have a frequency that is less than the color green, whatever be the intensity, whatever be the energy with which I shine that light, the electrons do not come out of the metal. So this is a photoelectric effect. You shine light on a metal, then electrons come out. So that is photoelectric effect. But then this happens for a particular metal, for a threshold frequency and above, but not for frequencies below the threshold frequency. But that should not be happening, as we just discussed, because, as we know, the energy of a wave depends on the square of the amplitude of the wave, not on the frequency of the wave. So, the wave theory of light could not explain the photoelectric effect satisfactorily. Compton effect is something similar. So, how do you resolve this? Many people tried to resolve this issue, but they could not succeed. Then it was left to Einstein to solve this problem. Einstein said this: stop treating light as a wave and start treating it as a particle. He said that each particle of light comes with a quantum of energy, a specific amount of energy, and that depends on the frequency. If the frequency is high, then the energy of the particle is also high. And he called those particles as photons. So the photonic energy depends on the frequency of the light. For example, if you take red, it has a range of frequencies. And for each frequency, imagine there is a photon. So in red itself, you have many different photons, and each photon will have its own energy level. And this thing will be this, the idea is the same for green, for blue, for yellow, and in infrared, or for ultraviolet light and X-rays, everything. So all these things have different photons, and each photon will have its own pocket of energy, an amount of energy. The photon is like a pocket of energy, and that amount of energy, as I just said, depends on the frequency of that light. So when this light, the photon, when it falls on an electron, the electron absorbs the light completely. It gets all the energy of the photon. And it tries to move away from the metal. Clearly, it has got energy now. So that gets converted into its kinetic energy, and it just tries to move. If the energy of the photon, of the electron, is sufficient to break free from the metal, then the photon just comes out. If the energy is more, then it breaks free from the metal and will also have some more kinetic energy. So the total energy of the photon is broken into two parts. One part is used to break free from the metal, and the other part goes to its kinetic energy, the kinetic energy of the electron. So it's like this. Suppose this is the electron, which is in the metal. So my fist is a photon. If I have a photon which has a lower energy, then what may happen is that it will knock off this electron. And if the energy is not sufficient, then the electron will not come out of the metal. But if it is sufficient, just sufficient, then it may just come out of the metal. At the same time, if the photon has a lot of energy and hits the electron with with that energy, then the electron that comes out of the metal will also have some kinetic energy. It will fly. Okay? So it will come out of the metal, and then it will also have some kinetic energy. That depends on the energy of the photon which hits this electron and gets absorbed by the electron. Okay? So this is what is called as the Einstein's photoelectric equation. It equates the energy of the photon with two things. One is the energy, the minimum energy required to break free from the metal, and the excess kinetic energy it will have. So the excess kinetic energy plus the minimum energy required to break free from the metal should be equal to the energy of the photon. He called it the work function. The work function is the amount of energy, the minimum amount of energy required for the electron to break free from the metal. So that's a work function. Work function plus the kinetic energy will be equal to the photonic energy. So this is how he solved the mystery. But then there is a problem. Well, the particle nature of light may explain this phenomenon, but what happens to Young's double slit experiment, where you had interference and diffraction? So those experiments clearly proved that light was a wave. Now you say that light is a particle, just to cater to this one, just to solve this problem. So if we consider light as a particle, then what happens to the wave nature of light? Well, that is also present. So light acts both as a wave and as a particle. It has both natures. It's both a particle and a wave. That is why we call it as the dual nature of radiation. Radiation is light. Then the question is, how do you know in a particular instance whether light is going to behave like a wave or a particle? It's like you seem to be doing some kind of an adjustment. You're trying to twist things. Well, not exactly. The way to know whether light would act as a wave or as a particle in advance is to ask ourselves the question, what is light going to do? Is it going to interact with matter, as in the case of the metal? So it was interacting with the electrons there, right? If light interacts with matter, then it will behave like a particle. If it does not interact with matter, then it will behave like a wave. So each and every place where light interacts with matter, it will behave like a particle. And each and every place where it doesn't have to interact with matter, then it will behave like a wave. This is the simple rule, to know in advance what you should do, to figure out what's happening. Some people are not comfortable with these two natures of light. And you may ask, how come? it's either a particle or a wave. How come it has both qualities? Yeah, it's like us, like you. Well, you may be an obedient and a perfect student at school, the darling of all teachers. But back home, you may be creating a ruckus. Your parents may have a difficult time handling you. Or it may be the other way around. Maybe you are such an obedient and well-behaved son or daughter in the house. But in school, you may be creating a lot of ruckus. You may be behind all the pun and fun and frolic and all troubles. So you have both the natures. Like you, light also has both the natures. The nature of a wave and also the nature of a particle. Under what conditions will it behave like a wave? We've just said. Whenever it doesn't have to interact with matter. Under what conditions will it behave like a particle? We've just said that too. Whenever it has to interact with matter. But it has these two natures. Does it have any other nature? We don't know. Nobody knows. As far as we can tell, light has these two natures. And we accept that. Because we have evidence to accept this position. So this duality exists with radiation, light. With this introduction, let's get into the lesson. The lesson in the beginning will have a lot of graphs. But if you understand this climax, and then look at those graphs in the light of this climax, and you will understand why the graphs look as they do. Why those experiments give rise to these graphs. Okay, the short summary of what we've discussed so far is this. There is something called as a photoelectric effect. So what it means by that is, when you have a metal which has free electrons, when light falls on that metal, then for a particular frequency and above, then electrons come out of that metal. This is a photoelectric effect. And this could not be explained by the wave theory of light. And it had to be explained by Einstein with the help of what is now called as the particle nature of light, with a photon picture of light. Now, Einstein said this. Suppose you have a metal like this, and you have free electrons here in the middle. They are moving in all different directions, but they cannot come out because of the reasons that we have just discussed. If they try to come out, then suppose an electron comes out of this, then this will become, the surface will become positive here, this is negative, so it will get pulled back into the metal. Then if light, if you're giving it, if you're giving the electron energy, then if it has sufficient energy, then the electron can come out of the metal. So that energy can be given by light. So you have light here falling, and these are the electrons. So when light falls on this metal and the electrons come out, and that is called as the photoelectric effect. Okay? And Einstein also said that light has to be treated like a particle, and it will have a quantized form of energy, which you call as a photon. So each photon, the photonic energy, each photon will have an energy which is equal to h into nu or f. Okay, so your book will give you h into nu. So this is frequency. Okay, so I'll use hf. Okay, so this is the energy of the individual photon. So the light has a certain frequency, as we've discussed in the wave theory, and for that particular frequency, then you can imagine that there is a photon, and that photon will have this amount of energy, and it's going to fall on the electron, and as it falls on the electron, it gets the incident light, the incident photon will get absorbed by the electron in the conductor, and the electron will gain energy. The energy of the photon will be transferred to the electron, and the electron will use part of the energy to break free from this metal, because it will have gain more speed, right? So it can go out of the metal. And if any more energy is left, then that would be the kinetic energy of the electron outside the metal. So simply, this E is equal to a work function phi naught, okay, plus the kinetic energy of the electron. So this is the photon energy, and this is the work function of the electron for this particular metal. So this will be different for different metals. Okay? An electron in cesium will behave differently than an electron in platinum, because it's surrounded by different numbers of protons and electrons. Okay? So this is the work function, or let's say the work function, the work function, and this is simply the kinetic energy. So this is what we have discussed so far. Okay, so keep this in mind. So light falls on it, light will an energy, the photon is an energy, packet of energy falls on the metal, and then it gets absorbed by an individual electron. Then the energy of the individual electron increases because it absorbs this photon, and the electron will use part of the energy to break free from the metal, can come out. It can gain enough speed to get out of the electrostatic force of attraction, and it can come out of this metal. And if the photon had any more energy than this work function, and that would be the kinetic energy of the electron. So you see, you shine the light, you see an electron coming back with certain kinetic energy. Measure the kinetic energy of the electron, and know what is the work function for that metal. For cesium it will be one value, for platinum it will be another value, for nickel it will be another value. So different metals will have different work functions. So if you know the work function of the metal and the kinetic energy of the electron coming out, and if you add these two, that must be equal to the energy of the incident photon. Okay. So the photon is completely absorbed by the electron, and that energy is used to do this. I keep repeating this because I want you to understand it fully. Okay. So this is a summary, basically. And I also said that light has both natures. One is this particle nature of light, and also the other is the wave nature of light. Both are present in light. Light has both natures, and that is the reason you call we call the whole thing as a dual nature of radiation, of light. Okay, so this is what it is. So with that, we'll get back to the story. We'll start the story from the beginning. In 1887, Hertz, the same guy whose name is present in the frequency of waves, Heinrich Hertz, he first discovered this phenomenon, the photoelectric effect. He saw that when you shine light on metals, then you can get electrons out of those metals. Okay, so that is Hertz discovered this phenomenon. And then there are many experiments which were conducted by other scientists. And two scientists whose names are very important in the history of this are Lenard and Wallachs. So they did a lot of experiments, and then they presented papers which contained the details of those experiments, which helped us form the picture of the photoelectric effect. So Lenard actually did what he did was, like, he had an evacuated tube. It's more like a vacuum tube, and with the vacuum tube, then he was able to demonstrate that electricity could be obtained from the metals using light. So it's like this. Suppose you have a tube like this, okay? It's an evacuated tube. It's an evacuated tube. So now you have inside the tube, you have two plates. So these are the plates. And now, let's say I have an ammeter which measures the current, and also a battery. A simple setup. Just try it. So do you expect current to flow in this circuit? Current will not flow. Why? Well, you see, these are the metal plates. They are not connected. So there is a gap between those plates, but they are more like a capacitor now. The two plates, it's separated by a distance, long distance here. And this is evacuated because, so you cannot expect too many, air molecules around. You can even say that, if there are too many air molecules, then you can say that by increasing this field, the voltage, the battery, and increasing the field between these two plates, you can ionize the air molecules, and current can flow. Okay? For example, if there is any vapor, air, okay, let's say there's an air here, let's suppose. Then you keep increasing this voltage, let's say this voltage, you keep increasing this voltage. So what happens is that the field inside between the two plates will also be increasing. So the field could be so strong that the air molecules here may be ionized. You can rip electrons apart from the air molecules, and then those electrons can. So if this is a positive charge and this is a negative charge, then clearly, the electrons that which are thus ripped will flow through this. So you can sense a current in this circuit. So the ammeter will show a reading. Okay, so that is why you are evacuating. You have an evacuated tube. So you are making it's almost a vacuum, so that there are not many electrons that are present. So the reason why you want to have an evacuated tube is because if it's not evacuated, if you keep increasing the voltage, the field value, electric field value can increase and ionize those air molecules. So you need to have an evacuated tube. So you have an evacuated tube. So now you cannot say that the field around, the air around it became ionized, and that is what was causing the current. There is nothing to contribute in the way of current in the circuit. There is a gap, and there is nothing between the plates now. Really, nearly nothing between the plates now. Now, you shine light on the objects. Okay. Then what will happen is, because you're shining light, the photoelectric effect will take place, and some of the electrons will come out on the plates. Now here this is positively charged, negatively charged. So these electrons will be pulled by this positive plate, and we can see a current flowing through this circuit. Okay. So Lenard did this. Okay. So it is a very important experiment in the history of photoelectric effect. Okay. And then Wallachs also did something, like he took a metal and then he did it in different ways. This is Lenard's thing. Okay. So Wallachs, what did he do? He did this, like he took a plate, a metal plate, I think it is zinc. Okay. Oh. First, like he charged it, negatively charged. This plate was negatively charged. Okay, already negative. Okay. So you can use an electroscope to measure the negative charge. Okay, or they had to give you an idea of how much negative charge is there in the plate. First, because he took the plate and then charged it. And what happened? Then he shone light on it. So shone light on this plate, then what do you expect to happen? For photoelectric effect, then electrons came out. So the plate started losing electrons. If it lost electrons, then what will happen here? If it lost electrons, then the charge on the plate will go down because the electrons have gone out of the plate. So you take a negatively charged metal plate, shine light on it. As you shine light, electrons will come out of the plate. So that the negative charge on the plate will go down because there's lost electrons now. Okay. So he did this first. And then this is the first thing. And second, he took a neutral plate and then again shone light on the plate. And what will happen? This also will give you electrons. Then what would be the charge on the plate? It was neutral, it has lost electrons, so this must become net positive. So using an electroscope, then you can measure, you can have an idea as to what charge you have. You can see that this has become positively charged. Okay. Then the third, he took a positively charged plate. We took a positively charged plate and then shine light again on it. What do you expect to have? You will still get electrons out, electrons will go. So this will become more positive now. So using an electroscope, you can see that the positive charge on this plate has increased. So they did this. So these two experiments are very important experiments in the history of in the history of the study of photoelectric effect. So Lenard and Wallachs experiments are very important for you. Okay. So Lenard used a tube, as an evacuator tube, a vacuum tube, and had two plates and did this and then made current flow. Otherwise the current couldn't have flown because it's more like a capacitor, you can see that. A battery, it's like you have a capacitor connected to this. The capacitor is kept inside a glass tube. That's how it is. Now, when you shine light on one of the plates, then electrons come out, then they get attracted by the other plate. So if you shine light on the negatively charged plate, electrons come out, You get attracted, flow. So the ammeter will show a reading. It will show that the current is flowing in the circuit. So even though there is a gap between two plates, the plates are not connected, they are separated, but still current flows. So you can sense it. And something similar was done by Wallachs. So these two experiments are very important for you. Oh, this is clear.